Welcome. In this video, I'm going to start going over solutions for the problem sets from Topic 2, Section 1. Question number 1 from the exercises asks, state two physical properties other than boiling point and melting point that would differ for the two isotopes of chlorine. Remember, the chemical properties are the same for the isotopes, but physical properties are going to be anything that are dependent on mass for the most part. So mass would be one. Obviously, the heavier, the bigger isotope, bigger numbered isotope has more mass. That's going to affect the boiling point and melting point, as already mentioned, but it would also affect the density. And the other thing it would affect as a gas is the diffusion rate. And those are probably the 5 most commonly mentioned physical properties. Number 2, explain why the relative atomic mass of tellurium is greater than the relative atomic mass of iodine, even though iodine has a greater number. So if you look, you see iodine is number 53 and tellurium is 52. Well, because what the atomic number means is that iodine at 53 has 53 protons. And it's telling us that tellurium has 52 protons. But the mass is both your protons and neutrons. So tellurium has more neutrons, which there's no reason it can't have more. So it just is letting you know tellurium, on average, atoms of tellurium have more neutrons than atoms of iodine do. Number 3 says, use the periodic table to identify the subatomic particles present in the following species. So I have lithium 7. Well, any lithium is going to have 3 protons because its atomic number is 3, which means it'll also have 3 electrons since it's a neutral atom. And then since the mass is 7, 7 minus 3 tells me there's 4 protons. Hydrogen 1 is going to have 1 proton and 1 electron, and it will have no neutrons. Carbon 14 has 6 protons and 6 electrons, and 14 minus 6 is 8 neutrons. Fluorine 19 with a minus 1 charge has 9 protons, but the minus 1 charge means it's picked up an electron, so it now has 10 electrons, giving us the minus 1 charge. And 19 minus 9 means it also has 10 neutrons. Fe56 with a 3 plus charge has 26 protons. The plus 3 charge means it's lost 3 electrons for a total of 23. And the 56 minus 26 indicates there are 30 neutrons. Number 4 is similar. It says isoelectronic species have the same number of electrons. Identify the following isoelectronic species by giving the correct symbol and charge. You'll need a periodic table. The first one's been done as an example. So really the key here is to look at the number of protons to identify what it is. So element 18 is argon. Adding up the 22 and 18 means the mass is 40. And then looking at the number of electrons, 18 and 18 means there's no charge. So this would just be argon 40. Element 19 is potassium. With only 18 electrons, it means it's a potassium ion with a plus 1 charge. And adding my protons and neutrons means it's isotope 39. And then element 17 is chlorine. The minus 1 charge, when I look at the electrons and protons, 1 more electron means it's a minus 1 charge. And adding the protons and neutrons lets me know it's isotope 35. Number 5, which of the following species contain more electrons than neutrons? So what I could do is, because these are mostly neutral species, I want to compare my atomic number to the difference between my atomic number and my atomic mass. So for the first one, hydrogen, 2, 1 hydrogen, 2 minus 1 means it has 1 neutron. This means it has 1 proton, and because it's neutral, it's also 1 electron. So this does not have more electrons than neutrons. 11.5 boron, 11 minus 5 is 6 neutrons. There's no charge on it, so that means there are 5 protons and also 5 electrons. So this has more neutrons than electrons. Part C, 16.8 oxygen with a -2 charge. So it has 8 protons, but the -2 charge is telling me that it's gained 2 electrons and has 10 electrons total. 16 minus 8 lets me know it has 8 neutrons. So in this case, I do have more electrons than protons. And 19.9 fluorine minus. Again, the 9 tells me there's 9 protons, but the -1 lets me know I've picked up an electron for 10 electrons. 19 minus 9 is also 10 neutrons, so only C has more electrons than neutrons. Number 6, which of the following gives the correct composition of the gallium-71 positive ion present in the mass spectrometer when gallium is analyzed? So if I look at gallium, I see that gallium is number 31. So I took a 31 in there, which if I subtract, that lets me know there's 40 neutrons. I know there's 31 protons, and because it's a +1, there should be 30 electrons. So B should be my correct choice. 5. Number 7, what is the same for an atom of phosphorus 26 and an atom of phosphorus 27? So the only thing that's changed here is the mass, which means the number of neutrons has changed. So the atomic number should be the same. The number of protons and electrons should be the same. But the mass number and neutrons will be different. So B would be my correct choice. The number of protons and electrons is the same. Mass number and neutrons are not. And number 8, use the periodic table to find the percent abundance of neon 20, assuming that neon has only one other isotope, neon 22. And this is a common problem that IB will expect you to do. They'll expect you to know if you only have 2 isotopes, we can call them X and Y, that X and Y then add up, the abundance of X and the abundance of Y adds up to 100%. Or X plus Y, I should say X percent plus Y percent adds up to 100%. Or if I convert it to a decimal, X plus Y equals 1, or Y equals 1 minus X. So knowing this, if I have X percent of 20, and I add it with Y percent of 22, that should give me whatever neon's average atomic mass is, 20.18. And I can then substitute in for the Y, 1 minus X will equal the 20.18. And when I distribute the 22 through and go ahead and solve, I end up with X being equal to 91%. And that means that neon 22 is the other 9%, with X being my neon 20. 7.5%. Number 9 is an interesting question. It says the relative abundance of 2 isotopes of chlorine are shown. You can see that chlorine 35 has 75% abundance, or 3 out of 4 isotopes should be chlorine 35, and the chlorine 37 is just 25%. It says use this information to deduce the mass spectrum of chlorine gas, Cl2. Well, Cl2 contains 2 chlorine atoms, so those 2 chlorine atoms could both be chlorine 35, or one could be chlorine 35 and one could be chlorine 37, or they could both be chlorine 37s. So the question is, what are the chances of each? Well, if you remember your math, my probability here is 3/4 and 3/4, so I can multiply those and my probability is 9/16 that they're both chlorine-35. Seems like pretty good odds because there is so much chlorine-35. Over half of them should be 2 chlorine-35s. My second one, I've got 3/4 of a chance of it being chlorine-35 and a 1/4 chance it'll be chlorine-37. So this would be a 3/16 chance. And my chlorine-37 is only going to be 1/4 times 1/4, or a 1/16 chance. If we add this up, though, we're only at 13/16, and that's because there's really another option. I could have the Cl37 be the first atom and the Cl35 be the second atom. So I really have to double this to 6/16. If I convert these to percentages then to do the mass spectrum, I end up with, I've got 56.25%. Sorry about that. 56.25% is the Cl35s. 6/16 is not quite as much, but it's quite a bit. And that's after I've added the 2/16 together. And then finally, the 1/16 is going to be just 6.25%. So then when you do your little chart, you're just going to have the masses down here. 70 would be the mass of 35 and 35. I'll just leave a space for 71. 72 would be a 35 and a 37. And then 74 would be both. And then I'd go ahead and show about 6.25% here. 37.5% maybe up here, and then the 50% up in that range. So something along these lines is what your graph would look like. And you could draw in the straight line like they often do. And this would be the percent abundance versus the mass down here. So that's what they were looking for on number 9. Number 10 then is a little bit messy, but it's very similar to the 2 isotope problems that we solved earlier. It says magnesium has 3 stable isotopes, magnesium 24, 25, and 26, with the lightest isotope having an abundance of 78.9%. So calculate the percent abundance of the other 2 isotopes. Well, what that means is if the 24 has an abundance of 0.789%, then what I know is that 25, the percent of 25 and the percent of 26 are going to be the other 0.219%, or I can do it like I did before. If I assume this is X amount, then this would be 0.219 minus X percent, and I can use those abundances to plug in with this. So I've got 24 times 0.789 plus I've got isotope with a mass of 25 times X, and finally an isotope with a mass of 26 times 0.219 minus X. And then I know that's going to be equal to 24.31 because that's the listed atomic mass for magnesium on the periodic table. So if I do that, I come up with magnesium 25, or X, having a percentage of 11.20%, and then that means magnesium 26 is the remainder from 21.9, or 9.90. You know what, I've got the wrong mass here. It's not 21.9, it's actually 21.1 is the number I want here. So 0.211 and 0.211 here, and that gives me the 11.20 and the 9.9 for the other 2 isotopes. So even though it appears you're solving for 3, you're really doing a 2 isotope problem again. Number 11, the Geiger-Marsden experiment supervised by Rutherford gave important information for the structure of the atom, positively charged alpha particles were fired at a piece of gold foil. Most of the particles passed through with only minor deflections, but a small number rebounded from the foil. How did this experiment change our knowledge of the atom? But the big thing is that it showed that there was a nucleus. It wasn't just this chocolate chip cookie with the electrons being chocolate chips embedded all around, and then the dough being the positive part. There's actually a dense positive center, or letter B, which was astounding to Rutherford and the others on his team. Moving on to the practice problems. Number 2 says, what's the relative atomic mass of an element with the following mass spectrum? So what you're supposed to realize is you've got 80% with a mass of 23, and you've got 20% with a mass of 28. So when you do that weighted average, you should come up with 25, or letter B. Number 6, which statements about the isotopes of chlorine-35 and chlorine-37 are correct? They have the same chemical properties. That's true of any isotope. They have the same atomic number. Also true. They have the same physical properties. Not true. So in this case, A, 1 and 2 only would be true. Number 7, which statement about the numbers of protons, electrons, and neutrons in an atom is always correct? The number of neutrons minus the number of electrons is 0. No. The number of protons plus, that would be true for the number of protons minus the number of electrons would be 0 if it's neutral. B, the number of protons plus the number of neutrons equals the number of electrons. No, that would equal the mass number. So here, if this was protons, it'd be a true statement. If this were mass, that would be a true statement. C, the number of protons equals the number of electrons. That should be true in a neutral atom. And the number of neutrons equals the number of protons. That may be true, but it's not always true. And then number 8, which quantities are the same for all atoms of chlorine? The number of protons, neutrons, or electrons. Well, the number of protons have to be, or it wouldn't be chlorine. And if it's an atom, then that also means the number of electrons. Number of neutrons, however, won't be the same, or there'd be no isotopes. So this would be B, 1 and 3 only. Number 10 asks, how many electrons does the ion 3115 P3- contain? Well, the 15 tells me how many protons it has. The -3 tells me it's gained 3 electrons. So normally it would have 15 electrons to match the protons, so we must be talking 18 electrons. So that would fit with D. And then number 11 on here, how many protons, neutrons, and electrons does the ion 2713 Al plus 3 contain? This is number 11. 2713 Al plus 3. So I know it has 14 neutrons. I can see it has 13 protons. And then the plus 3 means it's got 3 fewer electrons, or 10 electrons. So when I look for that, that would fit with C, 13 protons, 14 neutrons, and 10 electrons. Number 12, a sample of iron has the following isotopic composition by mass. Calculate the relative atomic mass. So they've given you all the information you need. You just have to set up the weighted average with 0.0595 times the mass of 54 plus 0.9188 times the mass of 56 plus 0.0217 times the mass of 57. And get your total, which I came up with 55.90, and the correct label would be AMU, or you could put grams per mole would be acceptable, although atomic mass, I take it back, should be AMU. And then the other way you could do it is if you don't like changing the percentages, you could take 5.95% times 54 plus the 91.88 times 56, plus the 2.17 times 57, and then divide the whole thing by 100 because that's really what your sample size is out of. Either way, you should come up with the 55.90 AMU. And finally, number 15, explain why the relative atomic mass of cobalt is greater than the relative atomic mass of nickel, even though the atomic number of nickel is greater than the atomic number of cobalt. So we've already had a problem similar to this. It's just letting us know that cobalt has more neutrons or has heavier isotopes. Or isotopes with more neutrons than nickel. And that's what's going to influence the mass. B, deduce the number of protons and electrons in the ion cobalt 2+. So if I look cobalt up, I see it's number 27, so it's got 27 protons. And since this is 2+, it means it's lost 2 electrons or has 25 electrons. And C, deduce the electron configuration for the ion cobalt 2+. So I have 25 electrons to put in. If I do the full configuration, it'd be 1s2, and then the second level would be 2s2, 2p6. And then the third level, it'd have 3s2, 3p6, and then I would expect it to fill up the 4s to get up to the 27. It'd fill up the 4s and then the 3d. Sorry, the 3d7. I had a little trouble finding it there. When I count cobalt over, I see it's 2, 4, 6, 7. So if it's 2+, the 2 that it's lost are the 4s2. So instead I'd have 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d7. Or you could have done this using noble gas configuration, and your noble gas would have been argon, and then I'd have 3s2, 3p6, 3d7.